Okay, welcome everyone to my continuation of what is algebra. Today I would like to tell you something about the so-called Jordan-Hölder theorem, sometimes also called Jordan-Hölder-Schreier theorem, depends a bit on the reference. And it's a theorem that kind of explains why simple groups are kind of the elements of the theory of groups. I'm going to explain what simple groups are, and I'm going to explain what the Jordan-Hölder theorem actually is. And along the way, I try to convince you that this is really like really this analogy to elements and compounds that I'm going to make in a second is really how you should think about it. So let's have a look. Let's get started. So I'm kind of want to sell this idea that whatever I'm going to tell you about it will be the elements of group theory, right? The kind of the easiest possible groups in some sense. And well, what could it be? So usually what you would do is, okay, you have a certain type of structure, a vector space, a module or a group or whatever it is. And as soon as you can find a substructure, you kind of can't call your object very simple or very basic, elementary, fundamental, whatever you want to say, because you can always kind of take a quotient and then you have something smaller that you could still study. And this is the whole idea. This is always the whole idea in some sense of what the elements of your theory are. Turns out you just have to be a bit careful what you mean by substructure. So for groups, there are usually two substructures that come to mind, just subgroups. And subgroups are certainly a substructure of groups. But it turns out that you can't really take nice quotients. So this whole idea of decomposing something into smaller pieces doesn't quite work for the notion of subgroups. So what you usually do is you look at something that is called a normal subgroup. And that's the right notion of a substructure in this context. That is a bit confusing, and if you see it for the first time, it definitely is confusing because a natural substructure, at least in my opinion, would be a subgroup. But again, I said again, it doesn't quite work. Quotients of quotient groups by subgroups are not groups anymore. That's the whole problem. You have to quotient by a normal subgroup to still get a group. And that's a property you want to preserve. So everything I'm saying today is actually concerned about normal subgroups, not subgroups. Um, but that doesn't matter in some sense because the main examples I will give, not quite, but the main examples I would give and that you should keep in mind will be for abelian groups. And for abelian groups, these two notions are the same. So for an abelian group, any normal subgroup is a subgroup. Anyway, this was kind of a disclaimer. So, and if you accept this notion of a normal subgroup for now, then what should be the easiest group? Well, the easiest group should be the one without, easiest types of groups should be the ones without substructure. So it should be the ones that, and they're called simple, where you only have the trivial substructures. So you always have G itself, of course, as a substructure, and you always have the trivial group, which I will just write as one. So don't get confused. One means for me is a trivial group. It's just so trivial that I don't bother to write anything else anymore. So okay, that was raffle. So let me start again. A simple group is a group without non-trivial substructure. You always have two substructures, the trivial group and the group itself, and you call a group simple if it's, well, if it doesn't have anything else. And here comes why. So let's say you have a normal subgroup of G. Then you can always form the quotient, and you have two things that are a real normal subgroup, right? So these two inclusions are honest inclusions. Then you can, well, you can always take the quotient, but what I'm trying to say is not true. These are not honest inclusions. Anyway, then they're always smaller, right? So the quotient is smaller in a reasonable sense, and the n is smaller anyway. So you kind of reduce the problem from G to studying G mod n and n. So two smaller structures. So, and that's the whole idea. That's why kind of, and you repeat this process until you hit those simple groups, because for the simple groups, you just can't play this game anymore. So these are really the elements of this theory. Here's an example, for example. So Z mod 12 is not a simple group. Why? Well, as I said, for abelian groups, not being normal or being a subgroup is the same. So I can just look for a subgroup. And certainly Z mod 6 is a subgroup of Z mod 12. If you wonder, for example, it's spanned by 2. So the span of 2 in Z mod 12 is Z mod 6. And I'm just simply writing Z mod 6 here. And both quotients, so you take this quotient here. This is, yeah, it really is 12 divided by 6. So it is Z mod 2. And the other one is Z mod 6, of course. And they are both smaller in some reasonable sense than Z mod 12. So no way you can't call Z mod 12 an element. But rather you repeat this process. You can't call Z mod 12 an element because it has smaller substructures. So you would repeat this process until you hit those simple groups. And I really would like to think of them as being the elements of group theory. Exactly in this setup, like you have a compound here, whatever this compound is, and those components are kind of your simple groups. So this simple group, for example, would appear 4 times, and this simple group would appear whatever 10 times apparently. And this is really how I would like to think about them. And because in the very analogy of having this as a compound, I could split off successively those copies here and go to simpler structures. So the compound is certainly not simple in that sense. In the same way, a general group won't be simple. You can always kind of split off simpler structures. And the whole thing I would like to make precise now, well, in this talk is that I would like to make precise in this video is whether this analogy really flies. So is there a group theoretical analogon of those, well, chemical formulas? Like you can split a compound into unique elements and basically in a reasonably unique way. So keep that in mind. So we want to split compounds into elements. And okay, technical thing, whenever I write this symbol, so the triangle pointing to the left in this case, I mean a normal subgroup, right? Because I just said normal is here the right notion in this context. You could think about subgroup, doesn't matter so much for this video at least, but just keep that in mind. And what you would do is you can start by composing things into smaller pieces. You can start with G, just call it N1. It's of course normal in itself. And there's a normal subgroup. Let's say you have a normal subgroup N2 of N1, and you have a normal subgroup N3 of N2, and you have a normal subgroup N4 of N3, and so on. Then you can take those successive quotients, and they are always smaller. So this is called a normal series. So that decomposes your group into smaller pieces. The example I showed you before was this one, right? And you get those 2 smaller pieces, Z mod 2 and Z mod 6. And now you realize, and I will make this, I have a much nicer picture in a second, but you realize that this is not simple. So this is not simple. So you can actually split this further. And that's what people then call a composition series, which is the main, well, as you can see, it's the main title of the slide. So you call such a series a composition series if all those successive quotients are elements, right? And successively, I could split off 2 at once, right, in a step, but basically I can make that finer and I can say, okay, the splitting of 2 at once was actually a splitting of 1 and then a splitting of 1. So you take this normal series, you make it finer, you call it a composition series. A technical assumption that you need also add is that actually those things are finite. So the normal series in principle could be infinite, composition series should be finite. But otherwise, it's really just you take the series of normal things that you slice off from your compound, and you demand that in each step you slice off an as small piece as possible, basically. So here is the sequence. So this refines, for example, into this one where this was a piece from before, but now in Z mod 6, of course, you have a Z mod 2 sitting there. And now your slices are Z mod 2, Z mod 3, and Z mod 2, which looks much better because these are simple. By the way, how can you see that Z mod P for P prime is simple? Well, you would need to look for normal subgroups, which, because it's a billion, you would need to look for subgroups, but because it's a prime, any subgroup would induce a, a splitting of the prime into factors, and it doesn't work, so there are no non-trivial subgroups. And the main question kind of you would like to address is, do these things exist, right? So that's basically, well, do I have those, do I even have a method to simplify my groups? Does it even make sense? And if so, are these things unique? So in some sense, what I'm asking is, are there prime numbers, right? Can I even talk about smallest pieces of numbers? Are there prime numbers? And if so, do I get a unique prime factorization? That's basically the two questions that I ask him here, and these are just answered by exactly the Jordan-Hölder theorem. That's what the Jordan-Hölder theorem is all about. So let me give you this bigger example to make sure that you understand the Jordan-Hölder theorem. So it's again Z mod 12. It's the same example, and I claim that there are basically three. So if you factor 12, so I would like to think of the following as the fundamental theorem of arithmetic, which is exactly this uniqueness of prime factorizations. And what does uniqueness of prime factorizations actually mean? Well, you can factor 12 into its prime factors, and I hope I did my count correct here, and it should be 3 times 2 times 2. And there are basically three ways of writing it. You can write 3 times 2 times 2, you can write 2 times 3 times 2, or you could write 2 times 2 times 3. They're of course all the same. They're the same up to permutation. And that's exactly what happens for the groups as well. So basically, those things are unique, and they're unique as it gets, but they can't be completely unique because you kind of have a choice of how to start factoring. So you have a choice of how to start slicing of those components. You could start here, you could start here, but up to this choice, what you will get is unique. So let's have a look at Z mod 12. So if you start with Z mod 12, you can, let's say you can slice off a Z mod 4, which is of course works because 4 divides 12, or you can slice off a Z mod 6. Okay, if you have sliced off a Z mod 4, then you can slice Z mod 4 further with Z mod 2, and then you're done. If you have sliced off Z mod 6, then you can again decide whether you want to slice off Z mod 2, or maybe I do a different color, maybe this one. You can slice off Z mod 3 and then you're done. But up to ordering, nothing changes. So let us have a look. I labeled here the edges by those composition factors, and the composition factors are exactly those things. So the successive quotients. So let's have a look. 4 modulo 12 is 3. So here's a 3. Let's see. 4 modulo 2 is 2. So here's a 2. 2 modulo 2 is 2. So here's a 2. Okay. 12, maybe I should erase it, this crap here. 12 modulo 6 is 2. So I see a 2 here. 6 modulo 3 is 2. So I see a 2. 2 modulo 2 is 2. So I see a 2 here, and you won't be surprised that the remaining ones are 3s. So actually, if you just, the order is different, but if I just read them in total, then I always get 3, 2, 2, 2, 3, 2. So I always get the same number, 2, 2, 3. So this is basically as unique as it gets. The statement is then that, well, maybe those composition sequences are not unique, but the factors you find up to permutation. And that's exactly then the statement. So the formal statement of the Jordan-Hölder theorem basically is the following. So if you have a finite group, then yes, composition series exists, which is not quite true if you don't have a finite group. So be careful. So yes, they exist. So you have a prime decomposition. In this case, they're as unique as it gets. They're unique up to reordering. So that's what I showed you here. But of course, I was completely suppressing that. They're also unique up to isomorphism. So I could write my subgroups. If I have a huge group, I can kind of choose different completely isomorphic subgroups to start with. So if you write uniqueness in anything related to group theory, it's always almost always certain that you must need to say it's unique up to isomorphism. Don't be too worried about that right now. The point is those decompositions are unique in the following sense. So this number, the n, is always the same. They have the same length. And all the composition factors, so all those are the same. Not in the, they don't come in the same order, but if you just collect all of them, they are the same. In other words, these are invariants of your group. Okay, it's a pretty nice theorem, right? It says it really justifies to think of simple groups as being the elements because, well, there's an essentially unique way to decompose your given compound, your given group into the elements. Just for completeness, I just said in the infinite case, it doesn't quite work, but as soon as you have a composition sequence, actually a B and C go through. But let's not worry about infinite things at the moment. Let's just say with a finite world, and then you get uniqueness, and so you first get existence, of course, and then you get also uniqueness in the best possible way. Yeah, just to wrap up, let me show you some examples of those elements, of those simple groups. Yeah, so let's start with a silly one. So some in older text, actually, one is considered a prime number. Nowadays, it isn't anymore, at least most of the time. But it's kind of a questionable thing, right? Should one be a prime number or not? With a trivial group, it's the same. Sometimes it's included as a simple group. Sometimes it isn't. Not quite clear. But it doesn't really matter. So the main meat are actually the following. So Z mod P for P being a prime. Why? I already told you if it's P times Q, so you can split so Z mod N for N equals P times Q, then you can always find a subgroup of order, well, P and Q, so this can't be simple. So the Z mod N's are simple if and only if N is a prime. So it's always Z mod P. And then it takes you a while. You need to go all the way to A5 to find the next simple group, which is not abelian. So, and then you get the whole list of alternating groups, which are simple. So alternating groups are elements of group theory. It's not quite the symmetric groups. Here's a composition series for the symmetric group. The symmetric group is not very far away from being simple, but it always has an alternating group, and it always has a quotient Z mod 2. Basically, I would like to think of this as these are the SN. It's not quite true. They're not quite the symmetric groups. They're the alternating groups. Anyway, there's two very natural examples of groups. So a Z mod P, arithmetic, right? Or let's say Sn. Okay, it's alternating groups, but anyway, let's say Sn. And then you almost find you have to look quite far to see the next one, but basically matrix groups such as a 2x2 matrices with determinant 1 over a finite field, because now you're over a finite field. So if my coefficients are out of a finite field, then I have a finite dimensional vector space over a finite field, so I have a finite set, and of course it is a group because you can multiply matrices, so you get a finite group. And these are those matrix group contribute the next series of examples of elements. They're not quite, again, the same as for the symmetric group. They're not quite simple. They have, for example, sometimes a non-trivial center that you need to get rid of. But anyway, they're basically simple. And then you have those funny examples, funny exceptions. There are only a certain number of them, 26. If you're really interested in learning a little bit more about this simple groups, there is a nice link in the description, which links to the so-called periodic table of simple groups, which was basically the main motivation for me to formulate things as I did. Like those are what I just show you on this slide, up to technical details, which are really very annoying. The elements of group theory are Z mod P, symmetric groups, and matrix groups. And that's a pretty nice statement in the end. But anyway, I hope you enjoyed the video. So Jordan-Hölder theorem is basically the justification why I would like to call the simple groups, the ones without normal subgroups, why I would like to call them the elements of my theory. Yeah, but that's it for today, and I definitely hope to see you next time.